Hello everyone, welcome to Deterministic Optimization. I'm co-instructor Andy Sun. In this module, we're going to start a new topic on large-scale optimization. We're looking at a very famous and important problem called cutting stock problem. This is our way to motivate large-scale optimization. So the learning objectives of this module is to discover new applications of linear programming in large-scale optimization and explore the very famous problem called cutting stock problem with large-scale LP formulations, and also discover algorithmic ways to solve such large-scale optimization problems, and it's called column generation technique. All right, so let's first look at an example here to set up the cutting stock problem. So imagine a paper company, a company that produces large amount of paper, for example, like this one. The company produces large rolls of paper, and a single individual can use this large roll. But for production economy, the paper is produced in large quantity, in very large roll. And each roll has a very large width, or you can think about this as the length of this roll here. In order to be used, satisfy demand, these large rolls need to be cut into smaller ones because demands come in as orders of smaller roll widths. For example, this big roll has, I don't know, 30 feet. The smaller rolls coming in much smaller width. This huge roll can be 100 feet, and the smaller rolls come in smaller width and different quantities. For example, the big roll of paper has width W equals 100 units, whatever that unit is, says 100, and the company receives orders from customers. The orders come in something like this. Customer 1 wants 150 rolls of width 25, a quarter of the big roll width. And customer 2 wants 200 rolls of width 35, for example. And customer 3 wants 300 rolls of width 45. So each customer wants a certain width and a certain number of rolls. So each roll has the same, you can say, thickness. The roll is, we're not differentiating thickness here. So when a customer wants 150 rolls of width 25, then that's a quarter of this big roll and the entire thickness, the entire quantity of paper in this quarter of the width. So in other words, the order is determined by a one-dimensional parameter, the width here, and how many such rows. All right, so the company needs to cut. So that's where cutting stock comes in, the name. We're cutting the stock of big paper rolls. For example, the width is 100, and this width can be cut into, for example, 35, 45, and 20. What is the total width? Well, that's exactly 100. So we exactly used up this row, of course. And we can write this way of cutting in the following way. So remember, the demand has 25, 35, 45 as width, right? So this way of cutting this one single large row can satisfy 1 unit of 35 and 1 unit of 45 with demand, but 0 of 25, right? So we're going to write this specific way of cutting as 0, 1, 1, okay? And this uniquely corresponds to this way of cutting because 0, 1, 1 means I cut 35, one row of 35, 1 copy of 45. Whatever remains is not going to be used, is waste. So that's exactly 0, 1, 1 here. So I'm going to call this way of cutting, specific way of cutting, a pattern to cut the larger roll. And a pattern is represented by this column vector. The first component is how many copies of 25 with demand are satisfied, how many 35, how many 45 satisfied by this pattern of cutting of one large row. Okay, you can do some other experiment. If we cut 2 copies of 45 width, then the remaining one is 10 units of width, and I satisfy 2 copies of the third demand and 0 of the first 2 demands. So this pattern corresponds to this column here. Again, everything is about cutting one big row to satisfy demand. And the column shows how many copies of different demand among the 3 demands are satisfied. For example, this one, I cut one big row into 4 copies of 25 width demand. So I satisfied 4 copies of the first type demand and 0 of the other. Okay, so you can see there are many, many ways to cut a large row to satisfy demand. And there are many ways to satisfy demand. For example, this is not a very economic way. It only cuts 25 to satisfy 1 copy of demand and throw away the rest. So I'm not using it to the rest of the width to satisfy any demand for type 2 and 3. Well, you can ask, why do you do that? Well, it is not a very economic way, but it is a feasible way to cut a large row into smaller ones and to satisfy demand, right? So any pattern that is feasible for cutting 100 width. For example, what is not feasible? If you cut 5 copies of 25, 500, that is not going to be a feasible pattern. So we are not going to consider those infeasible ways to cut the large row. So all of the feasible ways, feasible patterns are allowed. So what is cutting stock problem? The cutting stock problem is how should the company cut large rows to satisfy demand in the most economic way? There are different measures of what we mean by the most economic way. For example, you can say what is the most economic way such that the total number of large rows cut to satisfy demand is minimized. So this actually is going to be our objective. You can also ask what about the amount of waste paper, how to cut such that the amount of waste paper is minimized. And also you can ask what about smallest number of switches between different patterns, because a pattern needs to be cut by setting up machines to cut the paper. So different patterns need to have certain setup cost to shift from one way to cut to another pattern. So what about the smallest number of switches between different patterns? So we choose, as I said, to minimize total number of large rows used, and we're going to formulate this optimization problem in the next lecture. So this is famous cutting stock problem. Okay, let's summarize. We learned the cutting stock problem. We set up this problem, and a very important thing is the meaning of a pattern. In short, a pattern is a feasible way to cut a big row into smaller ones to satisfy specific types of demand. So that's it for this lesson. Thank you.